Okay, so this is our last video for section 4.2. I'll try to keep this one relatively short. We're going to introduce the idea of a basis. So far we've encountered the idea of a subspace, right? So really when we say basis here, we mean basis for a subspace. Okay. So what exactly is a basis? Well, we've kind of addressed the idea that any subspace, should be written as a span. So we look for a collection of vectors so that we can write our subspace as a span of vectors, because we know that any span is definitely a subspace, right? But we know that not all spanning sets are created equal, because if you work with a dependent set, then you have some redundant vectors in there, right? If you want to describe, let's say, a subspace, which is a line through the origin, you want to describe that as the span of a single vector. You wouldn't want to describe a line through the origin as the span of two parallel vectors, because that's just redundant. You want to simply use that one vector in there to describe your span. Similarly, if you're dealing with a plane, you would want to describe a plane as a span of two vectors. You wouldn't want to be dealing with three or more vectors. So a basis is basically what you take if you start with a spanning set and then you get rid of any garbage that's in there, you get rid of any redundant vectors, and what's left over once you throw away the redundancies is an independent set. So a basis is going to be a set of vectors which is independent and also spans your subspace. So here's the definition, right? So you have a subspace of Rn, and you have a bunch of vectors v. So the key thing here is that these are all vectors in v, right? So each vi is, when we say that's a subset, we just mean that each vi is a vector in the subspace, right? So I going from 1 up to k. So we want the span of this set to be equal to v, right? So we want v to be the set of all things that look like c1 v1 down to ck vk, where all these ci's are just scalars. But we want those vectors to be linearly independent. So what this means is that when you add the independence in, what the independence means is that, well, every v in v can be written. So every v in v can be written as a linear combination. V equals c1 v1 down to cn vn. This is the so the can be written. The fact that it can be written. This is the span. This is the spanning condition. The independence condition is that not only can it be written as a linear combination of this form, v1 up to, v k, it can be written uniquely. Okay, so the uniqueness here, this comes from the independence. Okay. The independence condition is what guarantees that for each vector in the subspace, there's only going to be one set of scalars that does the job. Okay, so you have both spanning and independence. This is what sets a basis apart from other spanning sets. All right, so here's an example. We want to find a basis for a subspace. Okay, so at this point, we might, the first thing we might say is, is it actually a subspace? Should we verify it? Well, we know what this equation describes. We know that this describes a plane that passes through the origin, and we've already discussed the fact that any plane through the origin can be viewed as a subspace. It is a subspace. If you wanted to verify that this is indeed a subspace, there's a couple of ways that you could do it. One would be to sort of say, okay, if I had v equal, let's kind of check things quickly here. Okay, so let's say v is equal to, let's say, a1, a2, a3. W is b1, b2, b3. So if I said that v and w are both in that subspace, well, what I would be telling you is that 2a1 minus a2 plus 3a3 has to be equal 0, and that 2b1 minus b2 plus 3b3 has to be equal to 0, right? Notice in particular that, 2 times 0 minus 0 plus 3 times 0 equals 0. The 0 vector is in there. And if you take two vectors of this form and you add them together, if you kind of add these equations, you can see that 2a1 plus b1 minus a2 plus b2 plus 3a3 plus b3 equals 0. And so what are these numbers? a1 plus b1, a2 plus b2, a3 plus b3. That tells me that that v plus w is in the subspace. And then you could do a similar argument for the scalar multiplication. But rather than kind of verifying things directly, we know that the other way you can establish that this set is a subspace is to show that it can be written as a span. So what I'm going to do is I'm going to say, all right, so notice that, so let's say my vector v looks like x, y, z. And I can solve this equation that I've been given, the equation of my plane. I can solve for any one of the variables in terms of the other two. Y looks like the easy candidate here. So y I can write as 2x plus 3z. Right? There's no reason I couldn't solve for x or z, but this allows me to avoid fractions. So I can write v as x. Y is now going to be 2x plus 3z. And then I have z. So I split this up. So I write one vector containing everything that depends on x, and another vector containing everything that depends on z. And then I can factor out the scalars. So this is going to be x. Let me move my equal sign. X times the vector 1, 2, 0 plus y times the vector 0, 3, 1. Which suggests that I should be able to give this as my answer. I should be able to give b equals 1, 2, 0, 0, 3, 1. Okay, why is that a basis? Well, this what we've done over here, right? So this tells me that my vector, my subspace v, is certainly the span of this set B, right? Because I started with an arbitrary vector v in my set, and I established that it can be written as a linear combination of these two vectors. So every vector in this subspace can be written as a linear combination of those guys. So every vector is in the span. So these two vectors, they span v. And we look at them, we can see they're not parallel. There's only two vectors, right? There's two vectors, they aren't parallel. So we know that B is linearly independent, and that tells me that it's a basis. Okay. One more example. Here's another subspace. Now I've written things in this form here rather than as column vectors. Maybe we should have done this sort of as angle brackets. But let's flip our notation. Let's stick with column vectors because that's what we're used to. This fits a little bit better on my page. So let's say V looks like. So what it looks like here, I've got 2x minus y, x plus 2y. X, and then minus x plus 4z. Okay? And so again, what I want to do here is I want to split this up. 2x, x, x, minus x. It's everything that depends on y. Minus y, 2y, 0. 0, that's all the stuff that depends on y. And z shows up down there at the bottom. Okay, so this is x times 2, 1, 1, minus 1 plus y times minus 1, 2, 0, 0 and z times 0, 0, 0, 1. Okay, so this suggests that my basis B should be 2, 1, 1, minus 1, -1, 2, 0, 0, 0, 0, 0, 1. Okay, and of course you have to do some checking. We know that it's certainly a spanning set. Why is it independent? One way to see that it's independent is to notice that you've got zeros in the third position for the second and third vectors, but not here. And so we certainly know that the first vector can't be written as a linear combination of the other two, and those remaining two are not independent, the remaining two are not scalar multiples of each other, they're not parallel. And so the three of them together have to be independent, because the first one is not in the span of the second and the third, and the second and third themselves are independent, so three of them together gives you an independent set. So then we know that that's a basis. By the way, one of the important reasons for studying basis is if you want to actually define dimension. Let me just make this as a remark before we end the video. The way you define dimension is the dimension of a subspace is the number of vectors in any basis. Okay. Now, there's a theorem you have to prove before you can make this dimension, or before you can make this definition of dimension. You have to prove that any other basis for this same subspace would have to have the same number of vectors. So whatever basis we choose, if one basis has 3 vectors, then every other basis would also have 3 vectors, because there are many possible choices of basis that you can make, infinitely many, in fact. But what's invariant across all possible choices is the number of vectors in that set. And so this is how you actually define dimension, right? So in this case, we could say something like this. We could say the dimension of V is equal to 3 because there are 3 vectors in that basis, right? In the previous example, there were 2 vectors in the basis, so we would say that the dimension is 2, right? And this sort of coincides with our intuitive notion, our intuitive understanding of dimension, right? That a line should be one-dimensional, and of course we can write it as the span of a single vector. A plane should be two-dimensional. We write it as a span of 2 vectors. Three-dimensional space, there it is, dimension in the name, right? So R3, we need 3 vectors to span all of R3. A basis will have 3 vectors. So this idea of dimension, it fits with our kind of common understanding of what dimension should mean. Okay, so I know those are some tricky concepts, but we're done with them for now. We're just introducing the ideas, like I said, at this point. We'll come back to these ideas later on in Chapter 6. We'll look at them from a sort of a more computational perspective and try to understand things in terms of systems of equations and try to get a better handle on things then.